Okay, so we're looking at the sticky situation lab, and what we're going to do, I'm going to go through a couple of the questions. I'm going to show you how some of the molecules are going to bond with water and some other things that came from your pre-lab questions part of it. And then we'll kind of go through most of the questions. So the first one asks you, why did you select the solvents you tested, and did your data support your hypothesis or disprove your hypothesis? Well, I'm not sure if all of you even looked at a hypothesis, but we're going to look at why some of the solvents would have worked the way they should have worked, and then we're going to look at the results that you guys got. Okay, so in the pre-lab questions, they ask you how water would bond with the sodium bitartrate, the sodium bicarbonate, and cornstarch, which all are, I think, part of cream of tartar. So if you look at your solvents that you have over here, this was from the second part of the lab. It says a molecular structure of typical solvents. We're going to look at these first. You can see that hexanes, which we have right here, this is what we call a hydrocarbon. Let me see if I can write this. Hydrocarbon. Okay, and the reason we call this a hydrocarbon is because this consists of all hydrogens and carbons. Okay, so there's no oxygens in there. Basically, this hexanes is very similar to gasoline or something like that. It's going to be kind of greasy, and you guys all know what gasoline does when you put gasoline on water, any type of oils, they float. So hexanes right here is not something that's going to, I guess it's not going to be miscible with water, so it's not going to mix with water. Then you have something like ethanol, and with ethanol, and you can see here with the 2-propanol, you guys have these alcohol groups, okay? And so these alcohol groups, they're going to allow this to interact with anything that can hydrogen bond, okay? So this also has polarity, if you guys remember that from biology. The difference is, you can see how this part of the 2-propanol, it looks like it's a little bit bulkier. If you can imagine that this would be a little bit, how do I want to say this, it would stick in the way a little bit more versus this kind of like a tail. And so because these can rotate, this is going to be able to fit closer to certain molecules than what this is. This 2-propanol here, this hydrocarbon group, is going to be more bulky. Then we have water, and you guys all know that water is very polar. And it's able to hydrogen bond because it's got the hydrogen is attached to an oxygen there. Okay, and then we have and water will bond with itself, which is why water has such a high boiling point that's 100 degrees C. Okay, you know, acetone here. This is fingernail polish remover. Or it's in fingernail polish remover, and what you can see, it does have this oxygen here, so it's going to be able to hydrogen bond. However, the hydrogens that are on these carbons here, they won't hydrogen bond. So acetone cannot hydrogen bond with itself, which is why it has a very low boiling point. I think it's like, I want to say like 57 degrees C. I'm not 100% sure on that. But it's really low, which is why you guys can smell it when it evaporates really fast. So if you're taking off nail polish or anything, you can smell it. Okay. Alright, so keep in mind that these are what these structures look like. And, whoops, let me get the other tool. Okay. So let me move this. Now, these were the structures that were in the pre-lab section, okay? So if you can imagine, water will work with any of these because we can have this, it's basically like a hydrogen bond. Okay, that's good there. So basically we get this hydrogen bond interaction here. And so I can draw this here, H, O, H, okay? So we'll get an interaction there. Another oxygen from water would interact with this hydrogen there. So you can see anytime you have an H and you have an O, you can see that you would get this type of interaction. So this is going to be soluble in water, okay? Same thing goes for your sodium bicarbonate. Now, when we get down here and we look at, when we look at this sample here, this was your cornstarch powder. Cornstarch doesn't necessarily dissolve as well in water because if you notice, this is a big molecule, okay? So it's able to do some hydrogen bonding with itself, but because it has a lot of these, you can see these carbon groups, these big carbon chains here, all of these rings, it's a little bit more rigid in its structure. But you could still have a hydrogen bond interaction like you would see right here. So we would be able to hydrogen bond there. You would have hydrogen bonding with water, as you can see right here. Okay, so all of those interactions, those will happen. So for the most part, you would say that the bitartrate and the sodium bicarbonate, they're soluble in water. The cornstarch powder is going to be a little bit less soluble in water. Now the question is, will these also interact the same with, let's say, I don't know, ethanol? So with ethanol, you would still have some hydrogen bonding, but it would be more along these lines where you'd have your oxygen, and then you've got your CH2, CH3. So you could get some hydrogen bonding there. Okay, but because this group is a little bit bigger, it's going to be a little bit harder for the molecules to line up, and so it's not going to be as soluble. Okay, so hopefully you can kind of see some of what solubility stuff that we're talking about. And then if I put in my hydrocarbon chain, so which is just, this was our hexanes, right? 1, 2, 3, 4, 5, 6. Okay, so this is our hexanes. This obviously won't hydrogen bond because there's no, off of each one of these, you have an H coming off of each one of those carbons, okay? So you're not going to get any hydrogen bonding, obviously. And because this compound here does have some oxygens, this hexanes isn't going to dissolve your cornstarch either. Alright, so based on what we saw before, again, these are our solvents, and what we're going to say is that your hexanes here, this is going to be nonpolar. Your ethanol is going to be polar. 2-propanol is going to be polar. Water is very polar. Okay, and then your acetone is also going to be a bit of a polar solvent. Okay, so basically all of those that have oxygens, especially those with oxygen and hydrogen attached to it, are going to be very polar solvents. So, okay, so when we talk about polarity, I keep calling these solvents as being polar. What this means is if we look at water, sorry, let me get the right tool here. If we look at water, okay, this is how the structure of it. And water has 2 lone pairs of electrons like this, okay? And so what we see is that because oxygen is very electronegative, it doesn't share its electrons equally with the hydrogen. So the electrons are actually, so there's in this bond right here, let me erase this bond. Alright, and so what we see in this bond is we actually see that there are 2 electrons being shared there, and over here in this one we have the same thing. We have 2 electrons being shared, okay? These electrons are actually closer to the oxygen, and so the electron density is pulled towards the oxygen. So instead of being here, we're going to say that these electrons are here. And what happens is this creates a dipole, and what we're going to see is that, let me do this in black. The hydrogen end ends up being positive, right, or a little bit positive, and the electron density goes this way. So what we see is that this is going to be what we call a partial positive. This is going to be a partial positive, and up here this is a partial negative, and this is a partial negative. So basically this is a double partial negative here, and over here this end is going to be partially positive. So it kind of acts, water is going to act like a bit of a magnet, okay? It's not a full positive because that's what we see with ionic bonding, because this is a covalent. It's just an unequal sharing. So this end is more negative. So you can imagine what will end up happening then is when I put another water molecule in here. So if I go here and let me erase all this. Oh, it doesn't want to erase all the way. Okay. So if I draw another water molecule in here, the hydrogen end is going to interact here with this oxygen end, because remember, this is a little bit partial positive and this is partial negative. So we get this interaction between these two. Okay, so that's just a brief overview of polarity, and we'll go through that later in the next unit or two. All right. So that being said, I can't erase all these. I'm going to show you a couple of the. I went ahead and I took all of the samples, the red, yellow, green, blue, and I put them into each one of the solvents. Okay, so take a look at the solvents that we have here. Okay, and I'm going to show you what they look like. Now, what they look like as far as when I did the chromatography in the different solvents. What I also want you to pay attention to is this. This group right here, you see how it has oxygens on it? That's going to give us some polarity. Okay, this has 2 lone pairs of electrons, which will allow us to hydrogen bond. Okay, here we can hydrogen bond because the water can interact with, so if I have an H here, O and an H, you're going to get this kind of interaction right there. So there's a hydrogen bond there. Hydrogen bond here, hydrogen bond here. Okay, same thing we see over here on the red 40. Definitely an alcohol structure, we can hydrogen bond there. Hydrogen bond, hydrogen bond, hydrogen bond, hydrogen bond, okay? Same thing here, 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 and here. So you would assume that most of these compounds should like any of the samples that can hydrogen bond, especially these right here, because if you look, here we have an OH, here we have an OH, here we have an OH, and in this compound here we have an OH, okay? So we should be able to see plenty of hydrogen bonding. Alright, so what you guys are seeing here, this is an example of all the chromatography. So you can see I took each one of the solvents there. So here's your red. Oh, why is it where? Oh, wrong side. So here's your red, obviously your yellow, green, and blue. And I did it for each one, and then listed above it I also have the solvents that I used, okay? And so remember, when we talk about chromatography, we talk about there's a mobile phase and a stationary phase. The mobile phase is what you see on the paper. The paper is your stationary phase, and your mobile phase is the solvent as it moves up, okay? So in most of these, we're looking for a separation of colors. So you can see with the water sample, and I let these run a little bit too long, like with this ethanol here, you shouldn't see it up here this high. So I didn't watch it very well, especially over here with this acetone. You shouldn't see it up that high. Remember, it should be about within an inch below the top of the paper. So obviously, if we look at this, it makes sense that it doesn't like hexanes, because as you can see, the hexanes, none of this traveled. So remember, the solvent is traveling up the paper, right? So you can see in hexanes, none of these moved anywhere, which means this sample did not like the hexane solvent, okay? So, which is no surprise, because if we go back and we look at the structure, remember the structure of hexanes looked like this. It had no possible hydrogen bond. It can't hydrogen bond at all with our dyes. So it makes sense that it's going to want to stick to the paper versus moving up the solvent. So hexanes would not have been a good choice for you guys, okay? As you can see, acetone, the red dye tended to like the acetone, which in comparison to water, if you look at this, you see how far this peak traveled up here? And then over here on water, it was one of the lower ones. So you would say that the red 40, so the red liked this solvent a little bit better. Okay, so it tended to like a solvent that was a little bit more nonpolar. Okay, and if we look over here, we look at the difference between your isopropanol and your ethanol. A lot of you can see that the blues, the yellow separated fairly well. If I was to choose which would have been the best solvent to see separation, I would probably go with ethanol. It looks like we got a little bit, because you can see that the green separated into a little bit of blue here and some of the green here, okay? You got red out of your yellow there. So I would say your best solvent for separation was your ethanol, because ethanol had properties of both, okay? Remember the structure of ethanol, it looks kind of like this, and then it's got it's got an O here and an H there, okay? So your structure of this looks more similar. It's still got the hydrophobic part, and then it's got the hydrophilic part. So alright, so when we go back to the structures that we saw earlier, this compound here is going to be hydrophobic, and if you have a phobia of something, you don't like it. So when we say hydrophobic, it doesn't like water. Alright, which would make sense why, if these compounds here, alright, they like water because they can hydrogen bond with the water molecule. So that's why you're going to also see that we get separation with ethanol and propanol. But what you want to notice is that we didn't see as great of separation with water, and that's because with ethanol, ethanol's got not only the hydrophilic part, it's also got the hydrophobic part. And in these molecules here, a large majority of these molecules, this right here would be more hydrophobic. So this would be more water hating right here and right here. Okay, in these areas here. So it would make sense that we would see decent separation with these two compounds because it's got properties of both. Alright, so what we're going to look at now is calculating the RF value. And so in order to calculate your RF value, this is going to end up being the distance to the middle of the spot over the distance the solvent traveled. I spelled that wrong. Okay. Anyway, so this is what we're looking for. So it's the distance to the middle spot over the distance the solvent traveled. Alright, so let me go ahead and erase this. Alright. So let me bring this back down. Alright, and so if you marked yours like you should have marked it, okay, you would have seen, let's say that your solvent line went to there. So you would measure from this first, where you made the pencil mark, right? Because that's where you put your dyes, all the way up to here, and we're going to give this an arbitrary number. We're going to say this is like 7.7 centimeters, okay? Now, the next thing we're going to do, if you look at, we're going to look at the yellow compound, okay, so the yellow dye. If you look, there's kind of a mark that's right here in the middle. It's a little bit darker. That would be the middle point of this yellow peak. So you can see yellow peak goes up to here. And then we have the red peak that goes to about there. So what we're going to look at is we're going to measure from the middle of here all the way up to that point right there. And then we are also going to measure from the middle of this to the middle of the red mark as well. So let's say this one, this first one with the yellow one, let's say that this was like 1.4 centimeters. So in order to get our RF value, we'd say 1.4 centimeters over 7.7 centimeters. And these units cancel out, and so we'd have our RF value for the yellow part. For the red part, let's say that that was at 1.9. Alright, so we would say 1.9 over 7.7 centimeters. And that would give us the RF value for the red part. And so the reason you do this is because within research labs, sometimes you want to be able to, when you publish a paper, you want somebody to be able to go back and repeat your results. And so in order to do that, they have to be able to know, they have to be able to take this solvent system, isopropanol, and they need to be able to run this TLC and know that if they get a spot at this RF value and they get another spot at this RF value, that they might have the same compound. Okay, so it's just one way to characterize the compound that you get. Alright, so I think most of what we've talked about should help you to answer the questions. This green chemistry one, it talks about it within the section, so you guys can go through and do that. We just talked about how to calculate this. So the only thing you're going to do is you're going to need to look at your data. If your data is not good, pick one of the other ones that I had in there and go through the data for the sample that I showed you. Let's see what else. Yeah, you should be able to answer most of that. So go ahead, I need you to go through the data collection and computation, and you're going to, the part that you're going to turn into me, you're going to write up that portion of it, okay? I also want you to turn in your observations as well. And then it says here you're supposed to write an explanation of how intermolecular forces and molecular structure of molecules being separated determine the ideal solvent used in chromatography, I can't even say it, separation. Be sure to cite specific evidence, okay? So basically, you're just going to go through and you're going to explain why the molecules separated the way they did and why certain solvents were better than others, all right? Now, your post-lab assessment. Whoops, I didn't want to do that. All right. So the post-lab, it says, write an explanation of why intermolecular forces would explain why pyridine is soluble in water and benzene is not. Alright, so what I'm going to do, I am going to show you the structures. You guys could look this up, but I'm going to be kind of easy on you here. Alright, let me get rid of these extra lines. Okay, so your structure of pyridine, it looks like this. Okay, those are 2 lone pairs of electrons. Oh, that's ugly. And then your benzene ring looks like this, okay? Structurally, this is how this is going to look. So you've got a carbon here, you've got a nitrogen, you've got another carbon, you've got a carbon here, another carbon, and then we've got a double bond here and a double bond here. So then coming off each one of these is a hydrogen. And as I was telling you, you have 2 lone pairs of electrons there. Over here, all this is, these are a bunch of carbons. Okay, and off each one of these carbons we have, alright, so coming off each one of these, this just moved on me. Alright, so we've got a hydrogen, we've got another hydrogen, 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 and in here we've got all these double bonds, okay? So based on these structures, you should be able to say why this one is soluble in water and this one is not, okay? Alright, that we're going to discuss here is what you need to do. So you need to do the data and assessment, okay? You then need to finish up, what was the other part? The argumentation. Part and whatever it was, documentation. Do that part. And then the post-lab assessment. Alright, and here's what you're going to do. You are going to type that stuff up and you are going to email it to, chemistry labs 22 at gmail.com. Alright, you have any questions, you can, I guess, contact me either in the classroom or on Edmodo. Good luck. Oh, I just deleted something I didn't want to delete.